I think it's a natural segue to go from talking about inspection and crack detection to WooYoung's presentation on die crack prevention and detection in advanced packaging. So WooYoung has more than 20 years experience in the semiconductor industry, and he works for a company that was, I didn't recognize, Onto Innovations, until he translated it for me as a merger between Rudolph Technologies and Nanometrics. So for many years, he's been active in the inspection business unit. And so thank you, WooYoung.
Okay, thank you for the introduction. Okay, so at the beginning of the conference today, we heard a lot about vertical integration. So putting multiple dies vertically to save spaces, and that's the new trend in the packaging world. So as we stack more dies vertically, the overall package's size, the thickness is going to be increased. The overall package thickness is by thinning chips or dies or reduce bump sizes. So, so in last 5-6 years, we've been getting a lot of requests from our customers for detecting die cracks, right? And that's because in the industry currently, these chips are grinded down. It's very common to see wafers grinded down below 100 microns, and we are seeing wafers that are even thinner, below 50 microns. So as these are as thin as below 50 microns, it becomes more fragile and susceptible to cracks and chippings, right? So what do we need to do? So we have to add on to innovation, we have a prevention and detection solution for all these chippings and cracks. So the traditional way of finding all these chippings and cracks is from a pick and place machine. So you take images from all 4 sides plus top and bottom, all 6 sides, and then find these chippings and cracks. But if we could find these at the wafer level, you know, that would and find all these defective dies at a wafer level, then it will save time and money. If we mark them as defective dies, then it will save time and money at the packaging at the downstream. Okay, so here I'm gonna show some examples of typical crack types that we see in industry. So the first one is what we call a hairline crack. So this is a very fine hairline cracks on top surface of a die. So this is what it typically looks like, and that's how it looks like from the side. And this is what some customers call it as a sideward cracks, or sometimes peeling or lamination. And the third type here is the inner cracks, and this is the most difficult crack to detect because on the surface it looks good. It's actually chippings or cracks going below the wafer surface or die surface. So it's very difficult to detect. And the fourth one is a backside crack. So this is a crack that happens on the backside of the wafer, but doesn't really continue up to the top surface of the wafer. So as you can see, these are pretty much all initiated from the die surface. And why is that? Because a lot of these cracks are initiated by the sawing process. Okay, so, and here are some more images taken from a side. So these are typical cracks and chippings look like. So why is it important to find these chippings and cracks? And that's because At the final test, these may pass electrical test and shown to be electrically good dies when they get packaged and assembled. And in the real world usage, these cracks may turn into a real breakage of a die and create a failure of chips. So it causes a long-term real-world usage reliability. So that's why it's very critical to find all these chips and cracks. So what's the prevention, right? So like I said earlier, a lot of these chips and chippings and cracks are initiated by the sawing process. So if we control these sawing process, that would be the best prevention to not have these types of defects at all, right? So here are some terms that commonly used in the industry. So curve margin, that's the measure between the edge of a die to actual shearing of a die. And then separation is actually the distance between two dies. And then I have a third one called position, and that's the actual the cut position. So zero will be the zero be ideal, and that will be the center of the street between these dies. Okay, so here these are the terms that I'm going to mention throughout the presentation to explain how do we do a curve metrology or a control process. Okay, so after we do curve metrology, here's some visualization of the result we get. So this wafer map, color map is showing a curve position. So remember, curve position is how the blade went through. So zero will be the ideal location, and that will be the center of the street. So here we have a color map showing how the positions are varying throughout the wafer. And on the right side, we have statistics, right? So that's one way to look at sawing process. And next slide, I have another parameter called the separation. Remember, so separation is the actual distance between two dies. So separation will be sum of materials that has been removed during sawing process plus the actual amount of stretch on a film, right? So smaller the separation, it is better, right? So if you think about it, so smaller, the less material we move during the sawing process and more center we make the cuts, that will be the ideal sawing process. And that will be the ideal way to avoid all these cracks and chippings from happening. So here is another way to look at curve process variation or control. And this graph is showing curve position variation by cut direction. So on the left side, I have all the position variation on all the horizontal cuts, and then on the right side, I have all the position variation on the vertical cuts. So as you can see in this graph on this wafer, the vertical cuts were actually centered around the zero. If you look at the scale, the vertical cuts are centered around zero, which is better, while the horizontal cuts are centered around like a 2 micron below -2, right? So but this is another way to look at your sawing process, right? And determine what's wrong. So you can look at this kind of data and go back to your sawing machine and tune your recipes, right? Okay, so here's another look at your sawing process, and this time I'm showing a curve separation by cut direction. So on the left side, I have all the curve separation on the horizontal cut, and then on the right side, the same thing, curve separation by vertical cut. And you can see that, remember, the separation is the materials that has been removed plus the stretch of the film. So smaller the separation is actually better. So you can see the vertical cuts actually is centered around 35 micron, whereas the horizontal cuts are centered around 45 microns. So it's about 10 microns smaller on the horizontal cuts. Right? So again, you can look at this kind of result and try to figure out why is this happening on your wafer. Take it to your sawing process engineers and ask them to optimize their process. Okay, so let's go to next slide. And this is another look at the curve metrology results. So this time I'm showing a curve margin by cut line. So on the left half of the wafer, I have all the horizontal cuts. And then on the right half of the wafer, I have all the vertical cuts. And so remember, margin is the distance from the die edge to the searing on both sides. So I have every cut line, I have two results, right? Because I have dies on both sides of every street. So as you can see, for every cut direction, we can clearly see two signatures, right? And this is because a lot of the sewing machines are using two-blade system to increase the throughput, right? So all these sewing machines have two blades that starts sewing the wafers from each end of the wafer, right? So in this case, a lot of times we see a clear signature of two sewing blades. Okay, so what do we see here? What can we learn from these graphs? So the first one, let's look at the margin. So on the left half of the wafer, the margins are actually closer, right, compared to the right half of the wafer, right? So this is indicating the position is actually better. Meaning, so if the ideal case would be these two be identical, like the red and the purple signature, if they are overlapping, that means they are pretty close to each other. That would be the ideal case. And when it's non-ideal, the difference between the two will be larger, indicating the blades didn't go through the center of dies, right? So that's the one signature we can see. The blade on the left half of the wafer did a better job than a blade on the right half of the wafer. Also, we can also see that if you add the margin on both sides, you can see the left half. Actually, in this case, the right half is larger, indicating less material has been removed on the right half of the wafer. So maybe if this is indicating the blade may be going deeper on the left half of the wafer, and then removing more, creating more debris, and then removing more materials, right? So these are all things that are very important to prevent cracks and chippings from happening at all in the first place. Okay, here's another look at curve metrology result, wafer view. So this time I have a graph on the x-axis is representing a curve position. On the y-axis is actually showing a curve margin. So I have two separate wafers. On the right graph, you can actually see that the blades are centered better. Right? And on the left side, on this case, the blades are actually not centered, and they all have negative value, indicating for vertical cuts, our blades are actually centered toward the left, and for horizontal cuts, the blades are actually shifted downward. So, okay. So that's the curve metrology portion. So that will be what we believe as a best prevention method to prevent all these cracks and thawings from happening at all. Okay, so let's say if so with all the prevention, let's say we still have all these problems. So let's say all these hairline cracks still happen. So how do we find them, right? So on the left side, on the color image, this is showing a typical hairline crack from the die surface. And as you can see, this is very thin and has a low contrast. And in this case, this hairline crack has around -2 micron width. It's long, but it's very narrow. So something like this is very difficult to see with the traditional bright field and dark field imaging method. And on the far right, I have an infrared image. And even with the infrared image, these types of fine hairline cracks are very difficult to see. So we've been struggling to find these kinds of fine hairline cracks from die surface. And we had to come up with a new way to image to find these types of cracks better, right? So in the center, we have what we call as a high topography image. So basically, to give you more details, is the intensities are changing based on the topography of the surface of a die. And with that, we get a much better contrast on such a fine hairline cracks. And you can see the same hairline cracks so difficult to see on traditional bright field image, even with the IR camera image. But in the center, we have a height-based topography image, and we can get a much better contrast of the same hairline crack. So with this kind of a high contrast image, we get a lot better chance finding these types of hairline cracks. Okay. Moving on, so sideward cracks, right? So if you remember earlier on my presentation, I explained sideward cracks are cracks that are happening underneath the die surface, right? So if you look at them with the traditional bright field and dark field images, we cannot see these types of cracks because they are hidden underneath the die surface. So in the center, with the 20x bright field image, as higher the magnification it goes, the numerical aperture increases and the working distance decreases, and you get a better resolution, but it actually becomes difficult to find these types of defects. But as you go lower max, your working distance increases and numerical aperture decreases, and it's actually working out better to see these types of defects underneath the die surface. So we have a tool with various magnifications that we can use for the inspections and find these types of cracks that are showing up underneath the surface. And on the right side, we also have a IR camera on the same imaging system, and that when we look at so these confirms the presence of the cracks underneath the die surface. Okay. And here's another example of a sideward or inner crack. So in this case, even IR camera had hard time seeing the crack underneath the die surface. If you look at the image on the left side, that's the infrared image, and you can see very faint signature of the crack underneath the die surface, right? With the contrast that as low as that, it'll be difficult, pretty much impossible for any algorithm to find that kind of a contrast and look at it as a defect. But on the right side, we are looking at the same the inner cracks, and this time we're showing images with a high topography based image. So, we have an image that is showing a intensity based of a topography, and as you can see, it can detect a very sensitive, it can be very sensitive, slight change of a topography. And with that kind of image, we have a lot better chance finding defects underneath the die surface. And here is just another confirmation of a sideward or inner crack. So if you look at the images on the two images on the left side, that's the suspected area with the inner crack. And you can see the bright field image is also showing some contrast, whereas a topography image in the middle is showing a lot higher contrast on the same defect, right? And on the far right, the green and red image, that's actually a cross, the far right image is showing a cross section. It's showing that the crack, where inner crack happened, is actually about 1.5 micron below the surface where it didn't happen. So this is just a confirmation that what we find as a high topography image is a real cracks happening underneath the die surface. Okay. So, like I said, as industry is going toward vertical integration, there is a lot of effort to make wafers and dies thinner and thinner. And with dies and wafers getting thinner and thinner, we are seeing getting a lot more requests from our customers to find all these types of cracks. These types of cracks may not show up in a immediate electrical test result, but when they get packaged and used in the real world, there's a good chance that eventually these types of dies will break. Right? So, and on to innovation, we have a prevention and detection solution for these types of hairline cracks or sideward or inner cracks. Okay. All right, thank you. That will be the end of my presentation.
Thank you, WooYoung. So I have a quick question. A lot of people run long traces around their parts for electrically detecting cracks. Does that work?
So I didn't hear the last part of your question, Dave. So yeah.
I'm sorry. I have seen people run metal traces around the periphery of their die to detect cracks and chips, and they look for continuity of the trace. Does that work in your experience?
So in some cases, it works. So that would be real big cracks. So very large cracks can be detected that way. A lot of hairline cracks or a lot of cracks that happens underneath the die surface doesn't show up. We cannot find cracks like that way. Because if you look at them from the top, they all look good.
Seems like there's a common thread here among a lot of presentation. It depends.
Sure, yeah. Yeah,
so
it depends. Yeah.
Here's another question. I don't quite understand how kerf inspection can prevent the saw-induced kerf damage. Can you elaborate?
Sure. So like I said, So a lot of these cracks and sawings are initiated by sawing process. And if you keep your sawing process so that the materials that's been removed is minimal, as well as if you keep the sawing at the center of the street, right? That would be the best prevention for cracks to happen at all in the first place. So as your blade getting toward closer to the die and more deeper, and if more material's been removed, you know, you're getting closer to making all these cracks.
So what about other sawing techniques such as laser cutting? Is that likely to create more or less cracks?
So that's a good question. So lately we've been seeing what industry calls stealth dicing. So basically making a laser group and then straight to films to separate dies. And even with that kind of a process, we are seeing cracks, and we're getting requests from our customers to find cracks and chippings even from stealth diced wafers.
So as a test engineer, especially like with WLCSP, you know, the dicing is done after the electrical test. So, I mean, and I know it depends and it varies. I mean, are we talking, you know, what percentage of die have cracking if they don't inspect them? I mean, what sort of defect levels does the sawing process induce after test has been done?
So that percentage, the defect rate, I don't know. So I'm in inspection world, and so all the samples that we get from our customers, they all have defects. So they send us defective wafers only, and our goal is to find the defects on wafer. So the yield wise, what percentage, that you know, that I don't know. Yes, hard to say.
Okay.
So we touched on laser dicing. Laser dicing will induce heat affected zones or weaken the die. Can you detect that as well after laser testing? Obviously, it's not all good.
So so that would be a delamination, I would say. So yes, we can. So we get a request sometimes to find delamination. So it all depends. Some customers, so all that delamination is happening on the street, and depending on customers, some customers may not care about you know, color of a change of a color on a street, but some people do. And when we get a request like that, yes, we can find such a defect too.
And plasma dicing, I've never even heard that term before. What's the trade-off with that? Well, I know what plasma is, but
yeah. So I'm an inspection expert, and I'm not sure what plasma dicing is, and I don't know how that works. So
okay,
yeah,
thank
maybe
you.
someone else in the panel can know. Yeah.
Well, WooYoung, a quick question about, you talked about height topography images. Does your system have to take images at multiple levels, or is it just sort of like one flash, like
No,
a
we
video
use
frame?
triangulation technology. So we have a sensor that's shooting lights at a 45-degree angle, and then we have a receiver on the other side which is also at a 45-degree angle. So when signals coming down at that kind of angle, we can detect topography changes in single measurement. So we don't need to do a multiple height. Yeah.
Got it.
So
It's a one pass tool. Okay.
Yeah, just one pass. Yes.
in doing that, I would assume that the crack would become more visible at one temperature versus another, hot or cold. Do you actually use that to advantage or not?
So no, so the wafers we get are long after it's been cooled down. So we don't use any temperatures to control defect sensitivity or defect detection method. So
your test is all room temp?
yes, exactly. Pretty much all visual inspections are happening at room temperature.
Okay. Well, I think we've exhausted the questions for the most part anyway. One just came in, but let's go ahead and call it for today. Thank you very much, WooYoung, and thank you to all my speakers in the session today. I very much appreciate it.
I'd like to thank all the speakers, and I'd like to thank everybody who's attended. I think we've had great participation, a lot of interaction, some really great questions. Also need to thank our sponsors who've made this event possible. ASE, Advantest, GelPak, Mullbauer, Amcor, and Microcircuit Laboratories. Our diamond sponsor is ASE. They provide OSAT and EMS services, the whole range from design, assembly, test, materials, components, and logistics. And then we also need to thank Advantest with over 30,000 installed ATE systems worldwide, deep expertise, a large workforce, and been in the measurement arena for over 60 years. So thank you, Advantest. Also, thank you to GelPak, whose goal is to protect the world's valuable devices, both in manufacturing and in process and in storage and in transport. So GelPak, we appreciate your support. And lastly, we thank Mullbauer, whose specialty is factory automation and data to drive the manufacturing process. So we thank Mullbauer for their support. Once again, I thank everybody for attending. I hope everybody found this a worthwhile and informative event. Please send us your feedback. I'd love to hear it and hope to see you at a future MEPTEC or event and in next edition of Known Good Die Workshop next year. So I thank everybody and I wish you a good remainder of your day. Thank you.